So I didn't put an affiliation here because I've now retired twice. Once in 2019 and then a second time in 2024. And then when I retired at the beginning of 2024, the lab gave me a little bit of a retirement party, but that was really a way of signaling that they are never going to pay me again. So I'm retired, kind of. Anyway, I'm going to talk about a class of numerical methods I've been working on and off for a long time for handling, simulating PDEs and complex geometries, really 19th century physics, classical PDEs. All right, the starting point for all of this is finite volume methods for partial differential equations. And these are all methods that assume that the PDE you're solving can be written in divergence form. So here you have Poisson's equation written in divergence form. Divergence of some flux vector is equal to a right-hand side. In this case, the flux vector is given to you by the gradient of the scalar field, the potential. For time-dependent problems, you have them written in, it's typically typically time derivative of your primary unknowns, u, is plus divergence, customary notation is plus divergence of a flux function f is equal to 0. So that's the PDE, those are the PDEs you're solving. What are the, how do we discretize them? Well, it's easiest just to look at a little picture. So discretization of PDE is just to integrate the divergence of f over control volumes in space. So you have mesh spacing h, and you integrate divergence of f over this little control volume. And what you get is just flux balance. And this is an exact relationship. F is the average of your analytic f over a face, so FD is. Either on the left or the right, take the difference of that, take the difference of this, and that discretizes the PDE. So all the work goes into computing your quadratures, and all the approximation goes into how you choose the quadratures for F. We're going to generalize this in a moment. Here's an example of the kinds of things that one does. Very typical sort of thing you do is use the midpoint rule and then add corrections. All right. How do you represent geometries on rectangular grids, irregular geometric regions? Irregular boundaries are represented in this method by the intersection of your irregular domain with Cartesian cells. So here we have a rectangular grid, and you have some irregular boundary here, and this side is the side that you're computing on. So you end up with a bunch of things that mostly look like rectangular control volumes, but other places they're things that are subsets of boxes. Now, so you can still apply the divergence theorem to integrate over these irregular control volumes. Most of the time, though, most of the time, though, you're integrating this over your regular rectangles, and you know how to do that. Now, all of the work and thought that you have to do for these methods go into how you set yourself up to do the quadratures over these irregular control volumes, both in terms of what does that even mean, and then secondly, what does it mean in the context of specific PDEs. Now, just something that I'm going to state up front so that I make sure I not forget it. The reason for this kind of gargantuan picture with only a small amount of boundary is to illustrate why you don't even think about these methods, particularly when you get to 3 dimensions, without having adaptive mesh refinement. Because really, you're going to you may want to have a fairly fine mesh near the boundary just to resolve the variation in the boundary, the curvature, so to speak. Now, you don't need that fine a mesh all the way out here, so adaptive mesh refinement is an essential tool here. Okay, so how do we go about doing this? So here we have, again, our two canonical equations, Poisson and some hyperbolic system. So what does it mean to apply the divergence theorem over a irregular control volume? So now we have the exterior of this blue region here is the computational domain, and I'm going to have irregular control volumes. So here you have, they're kind of indicated by the black dots or the red circles. You think of the black dots as being as labeling the Cartesian cells that these things came from, and then the open red circles are the centroids of those regions. Now, so you can integrate f over each of these irregular control volumes and do, just scale things so that you can identify what's what. And here's what you get. The integral of divergence of f, which is meant to approximate 1 over kappa times h to the d. D is the dimensionality of the space, and that should be a capital D. And h is your mesh spacing. So we're looking at averages, not actual integrals. And when I apply the divergence theorem, what do I get? Well, again, do a little bit of scaling. 1 over kappa h times the sum of, these are fluxes on the faces. So here, for each face here, we have a flux. And then we multiply by a scaling factor. The scaling factor is what fraction of the boundary here is exposed. Then we have one more term, which is the average of the flux along the intersection of the boundary of your domain and the cell. So that's alpha b f dot n. And that is what we define to be divergence of FFH. So there's a possibility of substantial efficiencies and ease of use from a rectangular grid. Now, one thing that you will see in irregular computations or calculations involving irregular geometries for say, unstructured grids is a lot of work and thought being spent in grid generation. So the analog of grid generation here, so this is, Leslie drew some very nice pictures of good grid generation and bad grid generation yesterday. Here, grid generation is a very conceptually simple, at least, construction. I need to be able to compute the normal on the face, on the intersection of the boundary with the Cartesian cell. I need to be able to compute the location of the centroid of the cell, x, the open red circles, and I need to be able to compute the alphas, both the alpha s's, the fractions of the faces that are exposed, and also a non-dimensionalized form of the length of in 2D of this boundary. Now, you have to, I didn't quite completely fix this slide. You want stable and accurate discretizations. Typically, if you are looking for a p-th order method, you can get by with a truncation error of order of h to the p minus 1 to get order h to the p solution error. And that shouldn't be second order, that should be p-th order solution accuracy. And this is true for classical elliptic and parabolic problems. And it's true at least for L1 in hyperbolic problems. I'll give a little more careful discussion of at least a little more of the ideas behind why this is true, why we expect this to be true. So I said grid generation is computing these things. Well, there have been two approaches to grid generation, at least. The one that really got there first for really complicated engineering geometry was due to Atomistic, Berger, and Melton in their Cart3D code from 1998. So what they started with, they were doing computational aerodynamics. There's a celebrated calculation done with Cart3D of opening the tailgate of a C-17 while it was flying. And it got this team lots of kudos, and deservedly so. But the starting point for this is that you have polygonal representation of surfaces. That's kind of how engineers work on, certainly in exterior aerodynamics. Then to get from that these intersections, you actually have to be quite careful. And the techniques they ended up using were computational geometry techniques using adaptive precision arithmetic. So when is something on one side or the other side of a triangle? That's a well-defined question, but the answer, in order to get it to acceptable accuracy, requires a lot of care. We've gone down a different road, and this is implicit function representations. So this is a very simple idea. So you have a domain, your irregular domain omega is the set, so you have a scalar function phi, your implicit function. Your irregular domain omega is the set of all points x such that phi of x is less than 0, and the boundary of your domain is the set of all x such that phi of x is equal to 0. Phi is nominally defined everywhere, although you really only care about it near the boundary. But also, the normal is something that comes out very naturally from this. The normal is just the grad of phi divided by the norm of the 2 norm of grad phi. This representation is broadly applicable and available, and medical imaging data gives you some form of this. Digital elevation maps, when you look at a map, what are you getting? You're getting z as a function of h and y. Well, z minus h of xy is phi. So you get that from kind of commonplace mapping and satellite data. And that over here is an example of that. This was actually a picture of a grid generation that we did. We were at that time, we were talking to folks at the California Department of Water Resources, and they said, okay, how would you grid up the San Francisco Bay and Delta? And essentially, we used the fact that there's an implicit function representation plus some other tools to do a grid generation for the Bay and Delta. So constructive solid geometry is a term of art that maybe I'll talk about a little more in a moment. And various kinds of other imaging data. So this is kind of a neat thing that Mike Barad did. He generated kind of an embedded boundary representation of coral using CT scan data. Okay, now, the other thing about implicit function representation is that creating more complex objects from simpler ones is easy. And I'm going to put in a proviso, easy should be viewed as being in quotes, because there's a little bit of a problem with this we fix, but you have to fix it. So how do you take the union of two regions defined by implicit functions? Well, the implicit function that defines that union is just the minimum of the two input implicit functions. Intersection, phi for that intersection is the maximum of those two implicit functions. So this is nominally not hard. So let me talk a little bit about what I wrote down in the slide before last was really, if you look a little more closely at it, is really midpoint rule. So it really was second order accurate computation of the fluxes. How do you go higher than that? What does that even mean? So So according to the divergence theorem, again, I write down the integral of divergence is equal to the integral of the fluxes over the exposed coordinate faces plus the integral of flux dotted to the normal over the boundary. So to get a numerical representation, you replace these guys and these guys with Taylor expansions. That's what you do when you're living in a structured grid finite difference world. So I've written that down here. This R should be a P. So this is the sum over the Taylor expansions up to terms equal to capital P. And it's Taylor expansion about a point. In this case, I would choose for each of these points the centroids of these faces. Now, the important thing is that you're expanding about a fixed point, which means you can pull the derivatives in the expansion out of the integral sign. So all that you really need to compute these terms are these moments. Similarly, down here, when we're trying to approximate this, well, because n is equal to grad phi divided by absolute grad phi, it's defined everywhere close enough to the boundary. And so you can do a Taylor expansion of that. And that's this sum over R. And I'm doing a Taylor expansion of n, even though that sounds silly. Normal is only defined on the surface, but it extends smoothly off of that surface. And then again, this is independent of the areas over which you're integrating, and you have to compute moments. And then there's an error term, as you expect when you're doing Taylor expansions and quadratures. So grid generation is the same as computing a collection of moments on the bounding surfaces. Now, so how do we do that? All right, how do we compute moments? So what we do is we go back. So the subtitle of this kind of section is Stupid Divergence Theorem Tricks. And so the divergence theorem trick here is now we take as fluxes, I'm going to take monomials times a unit vector in some direction as a flux and apply that divergence theorem formula to what you just saw. So, and what I've done here is I've done that, and I've done something a little bit special. I pulled the, so let me go back. So I've pulled the AEB, the integrals over the embedded boundary over onto the left-hand side, and I've actually computed this guy over on the left-hand side for the monomial as well. So let me go forward. So I have moments over my whole volume of a monomial, of my whole control volume, minus moments over my embedded boundary is equal to moments over my surfaces, the flat surfaces 1 dimension lower, and moments over higher moments over the embedded boundary for the normals. So, why have I written it this way? Well, these guys here I think of as being hard. Why? Because this is the integral over a volume. Well, that's the integral of a monomial, to be sure, but it's the integral over an arbitrarily complicated irregular region. We don't really know much about phi other than we're assuming it's smooth. Similarly, we're computing the integral over the intersection of the boundary of that region with a rectangular cell. That sounds so that sounds like these would be hard. Well, they are hard. That is the point. particularly if you're going to go to orders greater than 2, second. On the other hand, what is it equal to? Well, it's equal to integrals over the same kinds of moments, the same kinds of objects, but 1 dimension lower. And I'll show you a picture in a moment that kind of summarizes this. And then you have integrals over derivatives of normals, and these are for moments that are 1 order higher. So how do you organize yourself to compute this? Well, for a fixed order, you think of these guys as unknowns, and these guys are things that you're going to be able to compute without knowing these guys, without knowing the left-hand side. So this is an overdetermined, it's a linear system for the moments. It's overdetermined in maximal rank. So we have a shot, so we can use, least squares and when you do least squares for this, I'll just a little bit of a throwaway comment here is that you don't do plain least squares. So kind of a lot of your life, particularly for elliptic problems, is you want to get some diagonal dominance if you can. And diagonal dominance translated into what's happening with moments is to kind of weight things that are closer to where you're evaluating the operator than farther away. So that's part of the weighting scheme. So how do we close the system? Well, for these higher things, at some point these things just become 0 because they're smaller than the truncation area you're aiming at. You're aiming at order h to the s. So we can replace these guys by 0. And that closes the hierarchy with respect to these. These are all 1 dimension lower. So what you do is you do the lower dimensions first, and then you use them to do the higher dimensions. Now, you apply this recursively to lower dimensional integrals. The 1 dimension case is really easy because that's just, computing moments on a line that intersects your level set, your 0 level set. So this, you really need, this really exploits in multiple ways the implicit function representation. The fact that we can do Taylor expansions of n makes things, just makes all of this feasible. And there are 2 flavors of this we developed. One was a paper in Camcos 2015. And I think really the cleanest version of this is due to Hans Johansson, and there's a discussion of it in the JCP paper 2023. And the reason this one is clean is because what he derives directly is a least squares problem for the interpolation coefficients for a stencil, if you like. And that kind of is kind of one shot with computing a Moore-Penrose pseudo-inverse. So here's the picture that summarizes this. So you have, here's your control volume, V. Here's the little piece of the boundary that you need to compute moments over, and you actually do use the moments over the control volume for other things when you're doing time-dependent problems. Now, what are the inputs for that? Well, the inputs for that are these things on the golden surfaces, which are 2 dimensions, and then you have to organize the calculation of this thing so that you do highest derivatives of the normals first. Now, so that says, okay, how do we do these 2-dimensional ones? Well, we apply the same algorithm, but in 2 dimensions, and then we have A that we have to compute, and S. How do we compute that? Well, that only involves the similar calculation in 1 dimension. Now in 1 dimension, we're great, because what are we doing? The moments over 1 dimension are going to be integrals over a line that intersects this line here from the one boundary or another of the of this surface, of this flat surface, to the zero contour. And that you can find by root finding. That's a one scalar root finding problem. So as I've stated, this procedure can fail. And here's a simple, obvious example. At some point here, I was doing a Taylor expansion of the normal. That implicitly assumes that the normal is not varying very much over your control volume. Well, consider what you get if you take a sphere that just barely intersects one coordinate surface. So this is going to be the intersection of the boundary with that coordinate surface, and the normal goes through all 360 degrees. So that assumption just fails dramatically. However, there's another nice thing about moments. Moments, one way of computing moments is to compute them you decompose the region over which you want to compute a moment, you compute the moments on each subset of that decomposition, and then moments sum to get the moments over the larger region. So that's what you do here is you just subdivide until you get an acceptable level of error in your Taylor expansion for the 2D normal here, compute the moments, and sum. And that basically, there are multiple versions of this kind of problem, and adaptive subdivision kind of fixes all of them. And they're fairly sparse. You can afford to do this calculation. Okay, so that's how we do, that's all of grid generation for any order. So the EB, so how about now that we have our grids generated, how do we discretize our PDEs? Well, in the embedded boundary approach, as I said, we have to be a little bit careful about how we choose our discretizations to make sure that we get things that are stable and that we get things that are accurate. And of course, stability is always the hard nut. So we're thinking of the applied PDE problems for 19th century physics are compositions of PDEs of classical type. So for hyperbolic PDEs, the consistent conservative discretization you construct, and then there's an obvious small control volume stability problem that's been known forever, and we have a particular way of fixing it, but there are other ways of fixing it as well. For elliptic PDEs, the small cell problem goes away because you scale if you're dividing by a small control volume and you're in your operator and you have a right-hand side, well, multiply both sides by that, and you're solving as the same linear system except scaled. So it's diagonal scaling of the linear system. You still have to be careful because not all discretizations are going to be stable. There's this whole make sure it's diagonally dominant. And for parabolic PDEs, you have to essentially use the things that you did for discretizing elliptic PDEs, and then apply some methylines discretization. So, if for second order accuracy, so these were all implicit Runge-Kutta methods. We used one that was due to, there was a written paper on which we used was Twizzle, Gummel, and Arrigo from 1996. And then for fourth order accuracy, then you go to fourth order additive Runge-Kutta, and that's Kennedy and Carpenter's treatment of that in 2003. So what is small cell stability for the hyperbolic problems? So you use some non-EB algorithm that's explicit. As a starting point. So the version when we first did this, we were using Godunov methods that were second order that are still, continue to be for shocks, still very hard to beat. And then we construct a consistent conservative discretization that kind of reverts to this in the full cell limit. So it's consistent, but it's not stable. Here, let me write down what this is. U at time n plus 1, I've discretized in time, is equal to U at time n minus delta t times the divergence of the flux function. Well, the divergence of the flux function is, the average of the divergence of the flux function, is delta t divided by kappa h times the sum of the fluxes over faces. It's this kappa. Kappa is the exposed volume. It's the volume fraction. We have no control over this. Kappa can go to 0. So we got to learn to live with that. So how do we live with that? Well, first of all, we say, well, if you have a small cell, don't do that. Do something else. So we construct a non-conservative scheme that is stable, and that's pretty easy to do. And we say un plus 1 is equal to un minus the non-conservative scheme times delta t plus some weight times delta t times the difference between conservative and non-conservative. So if the weight is 1, then you recover your conservative scheme again. If the weight goes to 0, if W goes to 0, if the weight is 1, you can recover your conservative scheme again. If W goes to 0 like kappa, then you get something that's stable. So, so the hybridized scheme reduces the conservative scheme in regular cells and is stable if kappa goes to 0, W's order kappa. Well, what's the problem with this? Well, this isn't conservative. However, I know how much mass I've lost. So how much mass have I lost? How much stuff have I lost? Well, here's just a little bit of algebra tells you it's minus 1 minus W times kappa times the difference of the divergence of the conservative non-conservative fluxes. Now, if you have been careful to create a consistent scheme for the conservative and non-conservative schemes, this is order H, or order H to the p minus 1. Now, you know how much stuff there is. You can take this amount of stuff and redistribute it to nearby cells that are large enough to absorb it. So, end of story. Except, you know, we all like to dink around with things, and there are. This particular one had the property that had the right limit as the CFL number, or what to me was the right limit at least, as the CFL number goes to 0. There are other properties you'd like to have that this doesn't have, and that's why people continue to look at this. Now, so that tells you about kind of the gross stability issues. How about accuracy? Well, this is the way we think about accuracy in our universe. So is all based on using modified equation analysis in a setting where, frankly, you have no business doing so. So the way you think about it is that you think of your numerical solution as being a solution, your exact solution plus an error. And what is that? So we define that to be the leading order term in the error. We define this modified solution, that is u plus error, as satisfying to leading order in H, du mod dt plus divergence of f u mod is not equal to 0, but it's equal to tau, where tau is the truncation error. So we have two cases here. So we're assuming we're hyperbolic, so that means everything looks like signals propagating. So here's a signal that propagates here, and what the signal is being exposed to as it propagates is the order h squared, if we're second order accurate, truncation error, until it gets to this irregular boundary. So it gets into this region where it's order h, but because the propagate, and then the wave reflects off and comes back out again, how long is this signal exposed to an order h error? Well, it's exposed only for a time order h divided by the wave speed. So that means the total contribution to this error is really order h squared. So that's if you have a non-characteristic boundary. If you have a characteristic boundary, something different happens, is that you have a wave that's propagating along this in this region that's kind of sticking to your irregular boundary, and yeah, you're going to get order h error. But it's going to be confined because the boundary is characteristic and the error is being generated right at that boundary, and nowhere else. So that means that you get order h on the boundary, order h squared in the interior for the characteristic boundary. That gives you order h squared in L1 norm. This gives you non-characteristic boundaries, gives you order h squared in max norm. This is not a rigorous argument, but it does tell us where to look. And you go and measure your errors, and sure enough, this is the behavior we see. So moving on now to elliptic problems. So modified equation analysis. So we've scaled. We can. Let me go back here. So if this were for an elliptic problem, we'd have we'd have something like this operator equal to a right-hand side. Well, I can multiply both sides by kappa, since what I'm doing is solving for something that's a function of the vectors, and that's actually enough to take care of the small cell problem. There are other issues you have to worry about for elliptic that are more subtle stability issues. But let me ignore those and just tell you what now that we're thinking about modified equation, tell you what the modified equation analysis for elliptic problems looks like. So here we have, we're solving, say, Poisson in a disk, and we have a truncation error that's order h near the boundary of the disk, because that's what we're representing as cut cells, as embedded boundaries, and in the interior it's order h squared. So modified equation says my error looks like the solution to Poisson's equation with tau being the right-hand side. Well, if you have a right-hand side that's order h squared, except on a set of, roughly speaking, codimension 1, where it's order h, then you get order h squared in the max norm of epsilon. And that's a little bit of elementary potential theory. And in fact, you can go farther than this. If your boundary condition is Dirichlet, then there's a standard superconvergence argument that you can actually do using potential theory and method of images that says you pick up 2 orders of accuracy. So you get order h squared contribution from the interior error, but actually the contribution from the boundary error is order h cubed. So, and these, as I said, these are all in max norm. So here is a calculation of, this is a Poisson on a sphere, or in the interior of a sphere. In the middle, we have the plot of the error, and here are the plots of truncation error and plots of solution error. And we are getting second order accuracy in max norm and solution error, and then we're getting advertised what we expect, what I just stated, for the truncation error. Now, the other thing that we need to worry about is how do we build solvers for this? And one of the things that me and the rest of the people who've been involved in this have been worried about is, well, what does multigrid mean in this setting? Well, again, it's a little bit tricky. But first of all, for multigrid, we're solving typically for elliptic or parabolic problems, which are elliptic by just after you discretize in time. You want to compute a solution to Poisson or to variable coefficient elliptic problems over on a nested hierarchy of grids. So you start out here. The colors, by the way, this was an illustration of, here's how we're doing parallelism. And you start out here on this fine grid, and you're going to go down, 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 solve on coarser levels, and then come back up again and interpolate corrections on the way up. So that's what multigrid is, roughly speaking. And how does it change when you're doing embedded boundaries? Well, first of all, in the embedded boundary case, and in fact, in almost all cases, as soon as you get past second order, you no longer have symmetric positive definite matrices. This is the sort of thing that leads us folks who do finite difference and finite volume to variational formulation envy. Because all the finite element folks, they say, well, we're in variational form. We get that for free. We have other advantages, though. So the matrices are not symmetric, but they're symmetric sufficiently close to positivity-preserving algorithms for multigrid to work. And you have to suitably define positivity-preserving for this sentence to make sense. It's not M matrix, it's something more general. But a key step in any case to these algorithms is coarsening. You have to define what you mean by coarsening your mesh. In the non-EB mesh, that's just geometrically coarsening. And for finite volume meshes, you say, okay, take some collection 2 by 2 or 2 by 2 by 2 collection of cells, and you coarsen it by turning that into one control volume. And that's not what happens, and it can't be what happens in the embedded boundary case. And here, this little cartoon here illustrates why. So this is a thin body, and the fine grid is centers of each of these control volumes and the black rectangles. Now, how do I coarsen this? Well, I'm going to coarsen just the way I decide to coarsen. I pick a 2 by 2 collection of control volumes, and I need to make them into a set of coarse control volumes. Well, what that means in this case is that you find so you think of your embedded boundary method as defining a graph where the nodes of the graph are centers of control volumes, and the faces of the graph are the faces of, or the arcs of the graph are the faces that connect them in an adjacency fashion. And you coarsen the subgraph consisting of all the points, all the nodes in the graph that are contained in this coarse cell. But what does that give you? Well, in this case, that gives you 2 control volumes. Why? Because nothing connects across this boundary, this region here to this region here. So you will get one control volume coming from these 4 fine control volumes, and one control volume coming from these 2 fine control volumes. So you have to, coarsening has to respect the topology of the finer EB representation, or it's just hopeless. And then things get even more complicated, not terribly, but a little bit. You have to think about it. When you're doing things like sharp trailing edges. So what constitutes the connected component? Well, it turns out that this guy over here is connected to here, even though it almost doesn't look that way. So it's slightly subtle, but if you think of this as being kind of coarsening graphs by some rule, then everything holds together. And here's an example of where we use multigrid, coarse, medium, fine, and this is error versus number of iterations, and we're getting multigrid type behavior for convergence. Okay, I've got 15 minutes left, so I'm going to now go through and show you some examples. This is the eye candy part of the presentation. Yes?
5 minutes left.
5? Oh, I only have 5 minutes left, and I'll have to go fast. I kept getting confused. I don't know whether it's 50 minutes or 60 minutes or 45 minutes. Okay, but I can go fast. So here's first set of things: shock hydrodynamics calculation, shock going over a ellipsoidal, an egg, and that's in 3 dimensions, and here in 2 dimensions, shock going over a ramp. And this is with an adaptive mesh, because you can see the adaptive mesh, the white outlines is where we have refined. This is an interesting thing, because here we have compressible Navier-Stokes on the left and compressible Euler on the right. So we're solving 2 different sets of equations. Well, which one of these is right? Well, by right can reproduce experiments. Well, it turns out that the one on the left is correct. And the reason is that, physically, is that the reason you get Mach stems in the first place is because too much mass is piling up in back of the incident shock, and you can't just attach a shock to the surface, so it pushes it up. The effective viscosity in the coordinate frame moving with this incident shock is to drag mass away from that reflection point. So it makes the reflection point, the Mach reflection region smaller. And this was, the computations were done, these things here were 2006. Graves and et al. Did the viscous versus inviscid calculations 2014. Why did they do that? Well, because Harlan Gloss and I wrote a paper with some experimentalists that did this problem here in 1985. And after 40 years, we finally got what we thought we would get if we could ever do compressible Navier-Stokes. Incompressible flow past a sphere. This is a Camco's paper in 2013, and this is small, modest Reynolds number, 600. But we're getting what is reasonable behavior. And again, this is to show that we can do adaptive mesh as well. Now, this is probably the thing that comes closest to being possibly of interest to people here, I think, so PDEs, solving PDEs in complex geometries, kind of on the micro scale or for very irregular geometries. So here we have flow through a capillary tube filled with crushed calcite. So this is all by David Trebitich, who is at LBL, and he's now kind of one of the leading experts in doing these kinds of calculations. Extremely irregular geometries. This is plots of the pressure on the surface of the calcite, O2 diffusion in aggregate soil. This was something he did when he was working with people looking at batteries, try to find for what is on the microscale, a very complicated tortuous lithium-ion electrode to find an effective medium properties. And the way you do this is you solve Poisson on this irregular thing in average. And then at a much larger level, this is flooding in a fractured shale. This one, I have 2 minutes, but I do want to do this slide, here's we're using these ideas for free boundary problems. So what do I mean by that? Is that there isn't one side to the boundary. You're solving a PDE on both sides, an elliptic PDE or a parabolic PDE. And so this is higher order accurate, so fourth order, and an elliptic PDE. What we're plotting here is the solution on top. Here's the truncation error. And you can see the truncation error is just dominated by what's happening at the boundary. You can see where the boundary is, right? On the other hand, when you plot the solution error, everything is smoothed out. So this is a very concrete example of what the modified equation picture is right. You can also use this this is a second order calculation for thermal heat conduction in a cartoon for fuel rods and nuclear reactor. And again, the main thing here is by actually computing something with legitimate jump relations and preserving the jump relations, you get around a lot of odd behavior when you try to apply multigrid with very large changes in the properties. So this gets it right without problems, and it's a classical problem, classical difficulty in just trying to capture it without explicitly representing the jumps. And I'm going to close with this one because it's just cute. It's something we did 20 years ago. So how do you compute diffusion on a surface? So what we did is we said, okay, first of all, we're getting, where's our surface coming from? It's coming from electron microscopy data, and that's represented down here, a bunch of slices. You take level set technologies, and you build up, you can build up a sign distance function representation of that surface. Now, sign distance function is exactly what we need, because what we're going to do is we're going to say, we will compute to approximate the diffusion on this surface. We will do volumetric diffusion on an annular region around the surface, a region that is of constant thickness. Well, that's what sign distance functions give you, right? So we pick a thickness. It has to be some small multiple of your mesh spacing. And the important thing here is that you're applying homogeneous Neumann boundary conditions at the boundary. Now, you would think, I mean, everything in sight is irregular cells, right? That's order H errors. how could I do better than order H? Well, it turns out this thing here, this Neumann condition, pins things down sufficiently that you actually get order H squared error, solution errors. And that was when we saw that, that was one of these little surprising miracles. And then we went back and did some analysis and showed why that was true. So this is my last slide. What haven't I talked about? There's a whole art to obtaining sign distance functions or implicit functions. And as far as I can tell, there are kind of two camps in this. Mathematicians like Stan Osher and Jamie Sethian, who solve PDEs, level set methods for Hamilton-Jacobi, fast marching methods for the Eikenall equation, to construct sign distance functions. And then there are computer scientists who will do almost anything not to solve a PDE. Don't quote me on this, except this is being recorded. So one of the latest things in computer vision is to get a sign distance function representation by using machine learning. And one of my PhD students actually did this, and then in her thesis, and for her last trick, she took one of the standard test problems, which is so this is constructing a sign distance function from 2D pictures taken at various angles around the building. And so what she did is she used one of the standard workflows for that, put it into the EB workflow for doing grid generation, and then solved Poisson's equation around the building. And this is what you get. There's a whole software thing that I have not talked about at all. And even at LBL, there are two major software products, EB Jumbo and AMRX. I would say that for embedded boundaries, this is still not black box. You need to collaborate with an expert to create a new capability. Or there are cases, we have a few examples, where people have seen this and they liked it and they became experts themselves. So I think I'll stop there. Thank you.